So now we are going to talk about finding a value of convergence for a power series. And so the ratio test is a test that's easy to use to test power series for both either convergence or divergence. You can also use the root test. I just think the ratio test is a little bit nicer. So we want to recall our ratio test. And the ratio test says that if we take the absolute value of the ratio of a term divided by its preceding term, and we look at that ratio's limit as n approaches infinity, that's going to give us some value rho. Rho is not the value of convergence, but if rho is less than 1, we can say that the series would be absolutely convergent. Rho is greater than 1, we would say divergent. And if rho equals 1, we say that the test, the ratio test for convergence is inconclusive. And just a note there, that P looking guy really looks more like a rho, okay? So I've drawn it there for you. So that is what we call rho. So let's look at an example here. In this situation, we're going to need to determine for what values does this power series converge. So on what interval is the series convergent? And the series that we are considering is the sum from 1 to infinity of -1 to the n minus 1 power times x to the nth power divided by n. All right, and so one thing we do when we start considering series, again, we almost always want to write out some terms, make sure we know what we're considering. So this would, if I listed my terms out, plugging in n equals 1, n equals 2, n equals 3, it's going to be an alternating series. My first term would be x. I would get minus x squared over 3 plus x cubed over 3. And that next term would then be minus x to the 4th over 4, right? So we see that pattern. So as we stated up above, we're going to do the ratio test. We're going to use that ratio test. So let's come up with what our ratio is. U sub n plus 1 over U sub n. So in that case, we would have x to the n plus 1 over n plus 1 divided by the term which would come in front of that, which would be x to the n over n. So I've got this large ratio. Remember, division by a fraction is multiplying, or the same as multiplication by the reciprocal. So I have x to the n plus 1 over n plus 1 times n over x to the n. X to the n plus 1 over x to the n, if I look at simplifying this piece right here, we would subtract exponents, and I end up with just an x in the numerator. So this is equal to the absolute value of x, and I can't simplify the n or the n plus 1. So my ratio, I'm going to go one step further here and say that this ratio is the absolute value of x times n over n plus 1. And so I have to leave x in the absolute value bars because I don't know what x is, but my n values are always going to be positive, and adding 1 to a positive number will be positive, so I can drop the absolute value bars there. So this represents my ratio, and what we know is we want to take that ratio and apply the limit as n approaches positive infinity. Now, I'm not dealing with x in my limit, so I can take the absolute value of x out in front, and whatever that x value is, I'm then going to multiply it by my limit as n goes to infinity of n over n plus 1. And this is a limit of a rational function which has a horizontal asymptote at y equals 1. So the limit we end up with 4 here. This limit turns into just 1. So I've got the absolute value of x times 1. And of course, I don't need to write times 1 there. Okay, so just to remind us, that goes to 1. So the absolute value of x, and that is equal to rho. Okay, so our definition, and I'll scroll back up and let us look at it, but our definition says if we do the limit as n approaches infinity of that ratio, and this is my simplified ratio here, that's going to equal my rho value. Okay, so just keeping that in mind, we wanted to do the limit as n approaches infinity of my ratio of terms, and that equals rho. So I know that if rho is less than 1, this is going to give us a situation where it is absolutely convergent. So in this situation, I have that my rho value equals the absolute value of x, and I want that to be less than 1. So if my rho is less than 1, we're going to be absolutely convergent. So that means somewhere here between -1 and 1 on that interval, when x is from -1 to 1, then my series is absolutely convergent. If my rho value is greater than 1, right? So I'll come over here and say, okay, well, if rho being that absolute value of x, if absolute value of x is greater than 1, then that means for x greater than 1 or x less than -1, greater than the positive or less than the negative, it's going to be divergent. Okay, so in this situation, now I've got, well, x is from -infinity to -1 or 1 to infinity. We know that it is divergent. Okay, so now I've got these intervals, but what we need to make sure that we do is we look at the end points of our intervals. We want to look at that -1 and +1 because we want to make sure we know what's happening right there. So far, I have not included those values in here, right? I've only got greater than 1, less than 1, greater than -1, less than -1. I don't know what happens at x equals +1 and at x equals -1. So suppose I let, if x equals +1, and I let x equal +1, and then I start plugging my n values into my series, I end up with 1 minus 1/2 plus 1/3 minus 1/4. Right? This is a harmonic series. It's an alternating harmonic series. And we know that an alternating harmonic series is convergent, right? It converges. The alternating harmonic series converges. And what about for x equals -1? So going up to my series and letting n equal -1, I get -1 minus 1/2 minus 1/3 minus 1/4, etc., which is the negative of, it's the negative version of a regular harmonic series, right? So this is a harmonic series, but it's the negative version. Anyhow, we know this diverges, okay? So before, earlier on when I said, okay, well, we know it's convergent from -1 to +1, that open interval, we actually have to change that a little bit. And my final answer here for where this would be absolutely convergent, we know that it is convergent for any x from -1 including positive 1. So it's a closed interval on that side. So the series converges from -1, not inclusive, to +1, inclusive, and then it is divergent anywhere else. So let's look at another example here. For what values does this power series converge? So we are dealing with the sum n equals 0 to infinity, n factorial times x to the n. So as usual, we list out a couple steps. I've got 1 plus x plus 2x squared plus 6x cubed, right? So that was just 0 factorial times x to the 0 plus 1 factorial x to the 1 plus 2 factorial x squared plus 3 factorial x cubed. Okay, so that's how we found those terms. And we're going to use the ratio test now to say, well, does this or does this not diverge, converge? So my ratio test, we're going to eventually do the limit as n goes to infinity of my a sub n plus 1 over a sub n, and that's going to equal some rho value. So my ratio right here would be absolute value n plus 1 factorial x to the n plus 1 divided by n factorial x to the n. And we have done some practice previously in our series section, but with factorials and simplifying them. N plus 1 factorial is the same as saying, well, n plus 1 minus 1 is going to be just n. N minus 1, take 1 away from that, n minus 2, and it keeps going. So n factorial, when I divide by that, that's just in there. So this cancels that factorial, and I'm left with, I need to find the limit as n goes to infinity of, I have n plus 1 in the numerator, and then looking at simplifying x to the n plus 1 divided by x to the n, we subtract those exponents, and that just leaves me with x. All right, so I get an x there. So actually, we have the absolute value of n plus 1 in here times x. So let's find this limit. And in this situation, well, I have the limit as n goes to infinity. N plus 1 is always going to be positive, so I can drop the absolute value bars from that and just have x in absolute value. And I'm not dealing with x here in my limit, so the x can come in front, and I've got the limit as n goes to infinity of n plus 1. And if I were to plug infinity in there, I would end up with absolute value of x. That limit is infinite. And because this represents an infinite limit, we're going to say it diverges. So let me rewrite that. Diverges. All right, so is that true? Is x times infinity always going to equal infinity? And we have one situation, there's one number that I could plug in here to multiply by infinity that would change it, and that would be 0, because 0 times infinity is 0, right? So what we know then is it is divergent for all x except x equals 0. And at x equals 0, the series converges. So there are some other examples in your text which you should definitely go consider, but what this brings us to is we have a convergence theorem for power series. Okay, so if that power series converges at some value C, as long as C is not a zero value, then we can say it will converge absolutely for the absolute value of all x less than the absolute value of all of the C. Okay? And if it diverges at some point D, then it diverges for all of the x values greater than that D. And that should line up with what we were just talking about in those past two examples.